continue our morning session with a talk by Kirone Mallick, matrix and Bethe Ansatz for the exclusion process. Thank you.
So, good morning to you all. Can you hear me? Is it working? Yes. And happy Diwali to everybody. I would like to thank Abhishek and Sanjeev for their invitation. It's a very, very nice place, and I'm very happy to be here. As Tomohiro was saying this morning, this is probably the most beautiful conference room we have ever seen, and it's very impressive and very, very pleasant. So I'm going to talk about the exclusion process once more. It's going to be a rather technical talk. I'm sorry for that. These are questions that we've been trying to work on for many years. So there's been a little progress recently, and I would like to tell you about it. But before going into quite technical and heavy stuff, I'm going to talk adiabatically to enter the subject, and just as usual, tell you about the importance of the exclusion process as a kind of minimal model for non-equilibrium, for systems connected, two reservoirs connected by a wire. And that's why we are interested in open systems, so typically two reservoirs at different temperatures, and a current which is conducted between the two reservoirs, and the open symmetric exclusion process is a good model for this situation. And again, I emphasize that we consider a finite system connected with some reservoirs which can make particles enter and exit the model. So this is a very simple model, but which has, of course, been studied a lot in the last 20 years. It's a paradigm for non-equilibrium statistical mechanics, and because of the exclusion, it's a hardcore difficult model. As most of you know, but I like to show this picture that I owe to Andreas Schatzschneider. The original model was not invented by physicists or by mathematicians, but rather by a group of biologists who wanted to understand how RNA is read by transfer, by molecular motors. And this model then has been studied in many different contexts. It is, of course, a special case of a driven diffusive system. It's a special model of the KLS setting models. It has been studied by mathematicians, but it has also some nice applications in real life. Okay, so now let's enter the technical stuff. One big breakthrough 23 years ago was done by Derrida, Evans, Hakim, and Pasquier, when they were able to express in a compact and handy way the stationary measure of the one species exclusion process with open boundaries. So I just recall you, for those who are not familiar, I imagine that almost everybody here knows about the model. We consider a continuous time Markov process on L sites, numbered from 1 to L. There is at most one particle per site. This is a classical model, but there is a kind of exclusion principle going on. It's a continuous time system. At each time, between time t and t plus dt, a particle can hop to the right or to the left with different rates a priori. Q is less than 1, but hops in which two particles would be on the same site are excluded. This is not allowed. And then there are two reservoirs on the left and on the right. Particles can enter with rate alpha, can leave site 1 with rate gamma, and the similar things happen on the last site L. So there are 2 to the power L configurations in the system. It's a binary string. And if you go to the stationary state, there are 2 to the power L stationary weights that should be computed. And these weights are not given by any kind of Boltzmann weight. For the finite system, it's a purely combinatorial problem, if you wish. And the solution of this combinatorial problem can be expressed by using the so-called matrix Ansatz. So the idea was the following, the idea of Derrida et al. If you take this configuration, so it's a binary string that you can write as 0, 1, 0, 1, 1, and so on. And this binary string has a weight. So the idea is to replace zeros or empty sites by a matrix E, occupied sites or ones by a matrix D. So for example, this configuration can be written as E, D, E, D square E, D, E, D, D. So this is a product of matrices, formal matrices D and E, and the stationary weight of this configuration can be computed as a matrix element of this matrix product. So this is written like here. A configuration is a product of D and E's, and if you evaluate the matrix element between a bra W and a ket V, this will give you the stationary weight of this system. So of course, W, V, D, and E are not arbitrary. They have to satisfy an algebra, and if this algebra is well chosen, it will solve for the stationary measure of this system. So this looks like kind of magic, but this has been developed by many people, for example, by Gunther, into a general method to study one-dimensional diffusive systems of this type. And what is behind the algebra of D, E, V, and W is a set of recursion relations between these different system sizes and a combinatorial structure. And this is the kind of thing we are going to talk about in more details. So first of all, the D, E, V, and W, they are not arbitrary. They satisfy quadratic algebraic relations. And if you choose D and E to satisfy this Q-deformed oscillator algebra, D minus QED is equal to D plus E. And if you choose the boundary vectors V and W to be eigenvectors of these combinations of D and E, these combinations that involve the boundary rates, then you can show that this algebra, if you take these expectation values on this algebra, these matrix elements on this algebra, indeed you are computing the stationary weights of your model. So because of Perron-Frobenius, the stationary weights are unique, so this is the solution of the system. Okay, so having that, you can do many explicit calculations. You can compute the phase diagram of the system, you can compute density profiles, you can calculate correlations. In the case Q equal to 0, this was done in the original paper of DEHP 22 years ago. In the case Q different from 1, it's much more difficult to do explicit calculations. However, this has been done by the end of the 90s, again by the German group, Gunther, Sandow, and other people, and in a very fine way for Q different from 0 by Tomohiro, who was doing his PhD at that time. He was able to compute current and stationary current and correlations for the general algebra here. So again, there's a nice review by Blight and Evans, which tells you all you want to know, almost all you want to know about this matrix method. This is a so-called matrix Ansatz. I mean, there is no general name, or matrix representation technique. And the main point is that this algebra encodes for some recursion relations between the weights and for different system sizes. So now comes, okay, so you can compute the phase diagram explicitly in the large size system limit. You can compute correlations. And one thing which is useful if you want to make explicit calculations is to find a representation for this algebra. And the representation involves Q-deformed Heisenberg operators. Typically, these are the typical, if you go to Q goes to 1 and you divide by 1 over square root 1 minus Q, you will get 1 square root of 2 or square root of 3. And this is nothing but the oscillator algebra AA dagger that we learn in quantum mechanics. So this is now kind of standard knowledge, at least in our community, and we want somehow to know a little more about these things. So I would like to tell you about multi-species exclusion processes. So these are works that things we have been working on for the last 7 or 9 years. So Arvind participated a lot when he was in Paris, in Saclay, a few years ago. Shikashi Arita worked on that. We worked also with Pablo Ferrari, Martin Evans, and Sylvain Prolac. So this is older stuff. More recent stuff that I've been working on with a group in Annecy, people from the integrable system community, Crampé, Ragoussi, and Vanica, is about the exclusion process with open boundaries, and probably I will not have time to tell you about some connections with current fluctuations, work that I did with Alexandre Lazarescu. So the real new stuff is the second part, but I want to recall you about these things, which are not so new, but not so publicized, to be able to tell you more about the open boundary case. So, multi-species models. So I told you about the one-species exclusion process, and then there are many generalizations to multi-species. Gunther told us about one generalization yesterday, but there are plenty of ways of putting multi-species and coining rules. So I'm going to tell you about one type of rules, which, to my opinion, is the natural one, because it arises if you take the basic exclusion process and you couple different exclusion processes, one species exclusion processes, you get naturally a multi-species model, which is the one I'm going to present you. And this coupling is a basic technique in probability theory. So somehow the multi-species model I'm going to tell you about is the natural generalization of the one-species model. So it goes as follows. So here, again, if some of you have worked on the subject, there's a big clash or war in the community about nomenclature, about what you call first species, zero, empty. So I'm going to choose one way of telling things, and if you are used to another one, please just translate it in your brain into this notation. There's nothing canonical here. So we consider a system with n species of particles. So now particles can be of different types, type 1, type 2, type n, and there are some empty sites. And we call empty sites holes or species 0. And the rules are the following. If you take a bond with a particle of species I and an empty site next to it, so I consider the totally asymmetric case here, only forward steps, then this particle I can exchange and jump forward. Okay? And now the rule is the following also. If I have a bond with species I and species J, then I can update and switch the occupancies, so go from ij to ji if the label of I, the class of I, the type of I, is smaller than the type of J. So in this game, particles of type 1, species 1, have highest priority. They are the fastest cars. They are the Porsches. Particles of type 2 are of secondary priority. They can overtake all other types but type 1, and so on and so on. Are the rules clear? So again, I mean, there is nothing canonical in this way of numbering things, but it's like a hierarchy. Type 1s are the most priority, then second, then third, and the less important ones are the type 0s, which are holes. So now if you think about this model on a ring, on a closed ring, and you put these particles, you have a multinomial number of configurations, and you can ask the same question as before: what is the stationary probability? What is the stationary measure of this model on a ring? So I'm considering a closed ring. So if there is a single species, only class 1 and holes, then the stationary measure is flat. It's easy to prove. There is no structure. If now you have two species, class 1, class 2, and holes, then again, almost 22 years ago, Derrida, Janowski, Leibowitz, and Speer proved that the matrix Ansatz allows you to compute the stationary weights. So now you have 0, 1, and 2s. And it so happens that you can compute the stationary measure by taking a trace over a quadratic algebra, which is very similar to the previous one. Don't forget that I'm considering the totally asymmetric case. So the first relation is the same one as the previous one. dE is equal to t plus e. And now we don't have boundary vectors, but we have an A matrix for class 2 particles. And the A matrix satisfies a very simple algebra with the D and E matrices. And in fact, you can realize this algebra as a special case of the previous open species, open one-tazep case. So it's, in fact, it's nothing but an avatar of the previous problem of the open AZEP solution. But using this algebra, you can compute steady state properties. You can prove, this was done by Jean Spear, again 20 years ago roughly, that the limiting measure is not a Boltzmann-Gibbs measure. You can compute correlations and so on and so on. So now the natural question comes, how can you generalize this construction? How can you find the stationary measure for more than 2 species, 3, 4, 5, n species? And the situation remained blocked for almost 20 years, for 15 years. There was no real way to generalize this quadratic algebra to 3 species and more. Okay? So the solution was in fact found by, so sorry, I'm just telling you about the matrices. So they are very similar as the previous matrices, but more than 3 species case remained unsolved for almost 15 years. And the solution did not come from this direction, but rather from a more mathematical and combinatorial construction that I'm going to tell you about, which was done by Ferrari and Martin, James Martin and Pablo Ferrari. So the construction is a bit involved, but it's quite beautiful. So I'm going to tell you about it maybe at a slower pace, because I think even if you don't, you will probably never work on that, but it's quite elegant and it's worth seeing at least once. So the idea is the following. So we want to consider, so what Ferrari and Martin did is that they first revisited the 2 species case. I told you the 2 species case is solved completely. We have matrix ansatz, but the problem is that it was blocked here. So they just reinterpreted this solution in a completely different manner, in a fully combinatorial way, and their reinterpretation could be generalized to n species. So this was the breakthrough. So let's come back to the 2 species case. And so in principle it's on a ring, but I'm not very good in drawing, so just consider this is more or less periodic, but I draw lines, okay? So we want to understand how to compute the stationary weight of a 2 species problem, class 1, class 2, and holes. And we have P1 particles of type 1, P2 particles of type 2, and the rest is holes. And we want to understand how to compute the stationary weight of this configuration, of such a configuration. So the idea is the following. You now draw 2 lines, okay? And on the first line, you draw P1 balls, and you don't give them a color for the moment being. You don't give them an identity. And on the second line, you draw P1 plus P2 balls. Okay? That's the first step. That's easy. Now, the balls on the first line, I color them in black, and I call them first-class particles. On the second line, I have to, out of these P1 plus P2 balls, I will have to color P1 of them in black and call them first-class particles, and P2 of them in red and christen them second-class particles. So how is this done? This is done in the following way. So I read from left to right. And here on the first line, I have a black particle, a first-class particle. Yes?
In the second line, there should be some particles.
Sorry?
P1 plus P2 is?
So here P1 is 4 and P1 plus P2 is 7.
It's only the number of particles.
Yes, the number of particles without giving them an identity for the moment being. I don't know which one of them will be first class and which one of them will be second class. This will be decided now by the following algorithm. Okay? So now, out of these 7 particles, I will have to select 4 of them that will be first class and 3 of them which will be second class. Yes? So how will this be done? So I read from left to right, and this particle is a first class particle, and I will couple it to the first particle below it, which is either exactly below it or to the left of it. So this particle, will be joined, not joined physically, just, will be married to this one, and this one will become black. So this will be a first-class particle. Now this one, I'm not allowed to marry it to this one because it's on the right. I have to choose this one for it. So this one will become black also. This one will become black, and this one will become black. So now this procedure, I'm going backwards, will allow me to select 4 particles on the second line, which will be called first-class particles. Yes? Okay, so you're right. So it's supposed to be a circle, or what they did in the case of infinite line, this situation is not possible. There will be always, with probability 1, there will be always another one before you. Okay, so now the other ones, I call them second-class particle, and they are red. So that's a unique way of assigning an identity to the particles on the second line, knowing what's happening on the first line. Okay? And of course, if I move some of these particles, for example, if this one, I move it here, it will become red. It will not be married to this one if it goes to the right of it. So the idea of Ferrari and Martin is now the following. This is a configuration of second-class particles on the second line. This is one given configuration of second-class particles. In how many different ways can I construct such a picture by moving particles on the first line? How many different possibilities do I have to construct this picture, this assignment of the second line, fixed assignment for different possible first lines? The number of ways I can do this construction will give me up to an overall constant the weight of this configuration. So it's a purely combinatorial problem. Okay? Is it more or less clear? It's a bit contrived, but I think the procedure, when you work it out a few times, you understand how it works. Okay? So the major point is that this construction is not one-to-one. If I slightly change the configuration on the first line, I will still get the same second line. Of course, I should not modify it too much. If this guy goes here, I will get the same second line. But if this guy comes here, then this one becomes black, and I will not have the same second line. So the number of ways I can change things on the first line by keeping the second line fixed tells me the weight of this configuration. So yeah, up to an overall constant. Okay, so now if you look at precisely what you are doing here, you will see that if I have 2 red guys here and a certain number of 1s here, black guys, of course the black dots on the first line, they have to be confined between these 2 imaginary walls, because if they cross them, then the color of this one will change. So if you look at this picture more precisely and analyze the combinatorics, you will be able to reconstruct the matrix Ansatz. The DEA algebra precisely does this combinatorial work of enumerating the number of constructions you can do to have this fixed second line. And in particular, so these are details, but in particular, the matrix A is a projector. The matrices D and E are shift operators, and this is precisely what the combinatorics found by Martin and James Martin and Pablo Ferrari does. Okay, now the beautiful thing is that they've been able to generalize that to n species. Suppose I have a configuration with P1 particles of type 1, P2 of particles of type 2, P3 particles blue of type 3. They understood very quickly that one has to put 3 lines and to assign colors. So you first assign colors to the black ones, then you assign colors to the red ones, and the leftovers are 3 species, blue ones. And you could do that up to n species, okay? So you can generate the weight of this configuration with 3 species of particles by drawing all possible pictures of this kind that are compatible with the last line. And the question is, okay, this is a kind of very geometrical and combinatorial construction. Is there a way to construct an algebra which does that without having to care about different cases and so on and so on? So this is precisely what we did with Martin Evans, Pablo Ferrari. We were able to represent this construction, this combinatorial construction, as an algebra of matrices. So there is a matrix algebra which encodes for this procedure in a purely algebraic and combinatorial way. And one thing is that once you have this algebra, you can prove that you have constructed the stationary measure without using any combinatorial trick, just by algebraic methods. So in fact, this is a matrix ansatz for the 3 species problem on a ring and holes, 3 species and holes. So this is the generation of the old algebra found 22 years ago here. So you see there is a real step of complexity that comes if you go to more than 2 species, and that's why that simple guessing did not allow us to find the algebra in a simple way. Okay, so this is for TASEP, directed jumps, and the construction of Ferrari and Martin only worked for TASEP. You could not incorporate backward jumps in this combinatorial construction. But as I told you, the algebras D and E, they can be deformed. For example, we had DE is equal to D plus E, but if we had Q jumps, backward jumps, it became DE minus QED is equal to D plus E. If you do the same deformation game into this algebra here, you can construct purely algebraically the invariant measure of the n species PASEP. So you don't need any combinatorial construction, but you can do it by a purely algebraic technique. So no, that's lacking. In fact, we did it the other way around. Once we have the algebra, we can construct a combinatorial construction, but it is not beautiful because you see here it was very much directed. You read from left to right, but if you really want to reinterpret the Q-deformed algebra into a combinatorial structure, then you will have to do matching the other way around and put some weights that depend on Q, and it will become unwieldy. That's why they were not able to find it, in fact, from purely combinatorial manner. So that's a trick. If you deform the algebra, then you can construct a matrix ansatz for the n species ASAP. So now this was only for 3 species, but I told you we can do it for 4 or 5 n species. So the method behind that is that the matrix ansatz itself, so we have now n matrices, n plus 1 matrices in the n species case, because there are holes also. This matrix ansatz can be constructed recursively. If I know the matrices for the 3 species case, I can construct the matrices for the 4 species case, and so on and so on and so on. So you have to make a kind of hierarchy of tensor products. And so if you know the n minus 1 species case, you can construct the n species case by taking the tensor product with some special matrices, AGMs. So if I tell you what these AGMs are, you know how the recursion goes. So some of the important objects are these AGMs. So just to put it in a very fancy way, what we have been able to do is to lift the n species problem into the n plus 1 species problem. So we can construct the stationary state of the n plus 1 species knowing the one of the n species. So we have a kind of operator which builds a more complex ground state from a simpler one, and which commutes with the evolution of the system. This is supposed to be a commutative diagram. This is the evolution and the Markov matrix operator for n minus 1 species. This is the one for n species, And we have now a transfer matrix which lifts this n-1 species case into the nth case. And as I told you, the fundamental objects are not the matrices themselves, but rather these lifting operators that allow you to go from one problem to a more complex one. And these A operators, they do satisfy a kind of Young-Baxter algebra. So now we can more or less relate them to the basic updating procedure of your stochastic process. And we can construct them. So this is more what we did with Arvind and Shikashi and Sylvain a few years ago. We now have a general procedure for constructing these transfer operators from one problem with n species to the next problem with n+1 species. But remember, all that is for the closed system or for the infinite system. No open boundaries yet. Forget about this. Martin Evans found a very nice interpretation in terms of a queuing process. And for those who are aficionados, you know that even if we solve a small problem with 10 sides, we use infinite dimensional matrices, D and E. And in fact, these D and E do not operate on the configuration space, which is finite dimensional, but rather on a queuing process, which is attached to this configuration space. And that explains why they are infinite and why they have this shift operator form. So now let's go to the system with open boundaries. So I still have a few minutes left. So we, as I told you, the 2 T-zap, for example, let's come back to the 2 species problem, was solved on a ring. But one could say, okay, but I want to have reservoirs of particles of first class and second class. I want particles to enter the system, to exit the system. What can we do? So, for example, we would like to have particles of type 1 and 0, type 1 and type 2 entering from the left and exiting on the right, because we want to study open systems out of equilibrium. So I will maybe cut a long story short. How can we build a system like that with open boundaries that we can solve? So the idea was to try to exploit the integrability techniques. So we know that the system with closed boundaries can be solved, and the idea is to find boundary conditions which are compatible with bulk dynamics so that you keep the property of the system to be integrable. So just to summarize, the integrability in the bulk is related to the existence of the Young-Baxter equation and of the so-called R matrices. There is a whole structure which tells you that the system is integrable in the bulk. The integrability on the boundaries is related to the existence of boundary matrices, which are called Sklianin K matrices. And somehow it is known that the R matrix has to satisfy the Young-Baxter equation, whereas so this is the R matrix, whereas the boundary matrices have to satisfy a compatibility relation between the bulk dynamics and the boundary transfer rates. So these are called the Sklianin reflection equations. So what we did with the ANSI group is to classify all possible boundaries. So this is a kind of, brute force calculation, but which had to be done at least once, is to classify all possible boundary dynamics that are compatible with bulk dynamics and preserve integrability. Preserving integrability meaning that they obey these kind of matrix Sklianin relations. So in the end, this program was fully completed, and we were able to find all possible boundary dynamics, injecting particles from the left and extracting particle from the left, injecting particle and extracting particle from the right, that keep integrability. So this, at least for the 2 species exclusion process, there is no other integrable system with open boundaries. Integral means that you have a hope to solve it exactly. There is no other one but these 16 ones. There are 4 possible rules on the left, 4 possible rules on the right, and you can mix them in all possible ways. So previously, there were some cases which had been studied by Arvind, Joel Lebowitz, and Gilles Spear, and also by Douchy and Schaeffer, where they had semi-permeable boundaries, where particles of species 1 could enter and exit the system, but particles of species 2 were confined within the system. So these appear as special cases of integrable systems that we found, but now we even have more general rules, which are still integrable, where you can extract and inject all species of particles from the boundaries. And the simplest case we have is here, where you can inject 1 and 2s from the left with rate 1/2 and extract them from the right. So this is a totally asymmetric case which is related to that. So this is a system in which the boundaries are fully permeable and it is still integrable. And what is quite striking, I find, is that if you change slightly the rates here, for example, you may wish to put rate 1 here instead of rate 1/2. And you look at the system, simple, finite size systems of size 2, 3, 4, and you immediately see that there is no hope of solving them exactly. If you just put them on Mathematica and look at the stationary measure, there is no structure, no mathematical structure, no combinatorial structure at all. If you put 1/2, 1/2, 1/2, you immediately see, even though you're not able to guess the solution, you immediately see that if somebody is smart enough, he will find the solution. So here really integrability becomes visible. I mean, it's a very striking property that you can just check on systems of size 3 or 4 and you just see that it works or if it doesn't work. So of course, now that we have the simplest example, which is one special case of the general rules we found here, you want to solve it. It's not enough to know that if somebody was smart enough, he could solve it. You want to try to solve it by yourself. And this took us a long, long time. So we want to look for a matrix ansatz for this model. So we are looking for 3 matrices, x0, x1, and x2. And so this was mostly, the input of our friends from, my friends from ANSI, the integrable system people. So we look for 3 matrices, x1, x2, and x0. And their idea was that we should not look at them, but we should rather look at some building blocks of these matrices, which satisfy some, they look awful, but they are in fact very beautiful, quadratic relations. So there are 9 building blocks, G1 to G9, which in fact help you to construct x1, x2, and x0. So somehow the primitive elements are not the matrices that represent the particles, but rather some objects which satisfy quadratic algebras from which you build x1, x2, and x0. So this is abstract algebra that they satisfy that can be deduced from the dynamics of the system. And from this you can compute some simple things, even from the abstract algebra. And only very recently, Mathieu Vanica, who's finishing his PhD in ANSI, was able to construct an explicit representation for this algebra, and therefore to obtain an explicit representation for these 3 x1, x2, and x0 matrices. So, okay, I'm telling you about this work. Of course, it may look a bit dry, but I hope that I have convinced you that there are some nice mathematical structure, algebraic and combinatorial structure, and that we don't understand much of them. For example, we have been able to construct that, but it took a year to obtain this explicit representation. And clearly there is something to unveil. There is certainly a systematic manner to generalize this to the n species AZAP and to be able to get these representations in a logical way and also to use them to compute physical observables. I will just maybe rush in the last 45 seconds. So this is the end of the main part of the talk. So you can say, okay, what's the use of that? What can you compute with that? Well, one nice thing which probably I've been telling about, and I won't tell much about anymore, is that this kind of algebra appeared in a very basic calculation for the one AZAP. If you take the basic AZAP model, you may wish to compute the large deviation function of the current that goes through the system. And somehow, if you want to compute the nth cumulant of the current, you have to use the solution of the n-species multi-species exclusion process. I don't know why, but this is how we did it. We noticed one day, well, it took some time, that the n-species problem allows you to compute the nth cumulant of the current in the one-species problem. That's how the connection was made. And then using this kind of algebra, we were able to obtain, but this probably most of you, all of you already heard about it, we were able to obtain explicit formulas. So this is not purely a formal endeavor, but it can lead to some formulas in the end. And even some pictures and some very precise expressions for the variance or the skewness of the current and so on and so on. But the building block are the solutions of the n-species exclusion processes and the matrices which are related to them. Okay, it has turned red, so I will stop here. Okay, this is a kind of side work that I've been doing for many years, trying to exploit integrability for these generalizations of the exclusion processes. The progress is slow, but okay, by the help of many people, it does occur slowly and slowly, but it's not finished. I mean, I hope one day there will be a full understanding of the algebraic structure, combinatorial structure, and the constructions behind all these things. And probably in the end, it will be very simple and very clear. Although for the moment being, we are not completely in the dark, but somehow in a kind of semi-obscurity. Thank you very much.
Kirone, in the models you discussed, the exchange rates for all the allowed processes are the same. You also considered cases where these can be different?
So, different, but not as different as we... So integrability, this is a property we wanted to of course, to enforce. You remember in the case of the one species AZEP, all the exchange rates could be different. Alpha, beta, gamma, delta. In the case of the two species AZEP, there could be, I think, 6 different possibilities, but we have only 4. So we have a codimension 2 manifold of possible exchange rates that preserve integrability. So it's not, but if you go beyond, you lose integrability, which means, in my opinion, probably you'll agree with me, no hope of solving it.
Aware of this Karimi-Poor result?
So yes, so Karimi-Poor, it's a different generalization of the multi-species exclusion process, where the distance between 2 particles is a kind of hoping rate, and there he can solve. But it's a different multi-species exclusion. It does not enter into this framework. Yeah. But he can solve also things. Yeah.
Is there any hope of using integrability to get anything for the open partially asymmetric?
Oh yes. No, sorry. Here I only showed the totally asymmetric case because the formulas. No, you see, no. Here it's in fact partially.
No, in the bulk.
Here. Q is here.
No, in the bulk.
In the bulk, it's Q hops in the bulk.
It's really partial.
Yeah, it's really partial.
Okay.
But of course, the precise example I gave here, which is the nicest, the simplest, is for a TAZEP. But it's PAZEP, in fact.
So if you look at like steady state properties, I mean, is there any qualitative difference between the integrable and non-integrable case?
That's a very, very good question. So of course, people who do quantum, they are conserved quantities. I think in our world, which is the classical non-equilibrium, if I dare say so, I would say no. It seems to me that integrability points are not very special, or there may be some observables where bizarre things happen, but it doesn't seem to be the case. But this is an argument in favor of integrability. Because then you try to look at integrable points, you dig them out, you do calculation, and you have something which is, in fact, more general than integrability.
It's
No, I was The question is like for this model also one can write like the hydrodynamic equations, and it's like what Gunther did for the multi-species. I guess one can, right?
Yes, so exactly, I should have said that. It's just one of my conclusions. What would be very nice, but I dreamt about that listening to your seminar yesterday, would be to have an integrable point with multi-species, being able to compute something like the exponents and get the Fibonacci sequence. I mean, this would be nice to get the 5/3 in the case of a 3-species case, where you could do better on that, compute the gap and so on and so on.
Would be nice. What I can say straight away is that this model will not do it. This is purely KPC. This we could see by looking at the mode coupling matrices.
Yeah, okay.
Yeah, just out of curiosity, you can do it, I understand, for general Qs, the ordinary A set. Now, in the limit Q to 1, you get a weakly asymmetric process.
Yes.
Now, I've always wondered how the crossover between the symmetric model and the asymmetric one depends on the length of the system. Has that been studied?
Yes, it has been studied at length. Especially, I mean, there are different crossovers. So you have to tune the WASEP parameter, the asymmetry parameter, as an inverse power of the length. And there are typically two regimes. If this, so let's call it P is equal to half plus epsilon, Q is equal to half minus epsilon. So if this epsilon scales like 1/L, that's a kind of Edwards-Wilkinson type regime, but non-Gaussian, so it's not as trivial as Edwards-Wilkinson. And if it's 1/√L, then you enter the KPZ world. So the right continuous limit to get KPZ is scaling the asymmetry parameter as 1/√of the length of the system. The crossover to KPZ, yeah. 1/, yeah. So Sylvain Prolac, for example, has studied the large deviation of the current in these two regimes and obtained all crossovers explicitly.
Just one comment about the last remark in the conclusion in your slides. So you mentioned that maybe it would be very nice if we can find some systematic way of understanding and generalization. Right? And rather this year, so one Japanese group like Kuniba and Okado, maybe you already noticed, but they found some connection from between this kind of thing with the theory of crystal. And they have some interpretation of the matching of the particles in terms of the language of crystal.
Yes.
And they seem to be interested in generalizations, so they may lead to something new.
You're right. Yeah, you're right. Yeah, I saw that paper, but I didn't study it.
Okay, yeah. Just as a small.
Thank you. Yeah, it's a useful remark.
Okay, so then let's thank Kirone again.